In this segment, I want to talk a little bit about the ideal gas law. So we've talked about the ideal gas model, and recall that that is a model where we visualize a gas as being perfectly spherical particles that just have collisions with each other and the walls of their container. That's our ideal gas model. The ideal gas law is a little bit of math that we attach to this. And if you've had chemistry class, then you've probably seen this before. And our approach really is not much different than chemistry's approach, so this may be a review for you. So here we see, let's imagine in our mind an ideal gas. And in our mind, we're going to do a few things to it and imagine how that might change other factors. So, for example, here we see an ideal gas. And notice we've just represented this with 5 balls, but of course there's a gazillion in here. And so if we increase the temperature, well, that means that the particles are moving faster. Recall that the temperature is a measure of the average translational kinetic energy of the particles that make up a substance. So as I increase the temperature, then I'm increasing the speed of the particles. If I've increased the speed of the particles, then when they collide with the walls of their container, they exert more force. More force during those collisions yields more pressure. So increasing the temperature of my sample of gas will increase the pressure. If I took the same particles at the same temperature, but I decreased the size of my container somehow, well, guess what? Now they have more collisions with the walls of the container. Because the particles just don't travel as far before they hit the side of the container, there's just more collisions with the side of the container. Since there's more collisions with the side of the container, guess what? The pressure goes up. So decreasing the volume increases the pressure of your gas. Similarly, if I increase the number of particles in my container, I get more collisions with the walls of the container. More particles means a higher pressure. We can put all of these observations together in what is known as the ideal gas law. And it looks like this. PV equals nRT. This is the pressure. Be careful. Notice it is the absolute pressure. It is not gauge pressure. Here's the volume. Again, our standard unit for volume is meters cubed. We need to put in standard units if we expect to get out standard units. The number of moles in the container is represented with little n. R is the ideal gas constant. The other thing I wanted to point out is that there is a unit of energy that chemists often use, liter atmospheres. And if you write this equation in liter atmospheres, well, then the only thing that's different is just this R value. And just watch out. It has a number that looks similar but is different enough you'll get the wrong answer. So just be sure you check your units. Right? This is joules per mole Kelvin. And don't use the value that is liter atmospheres per mole Kelvin. Okay. So this R value here is 8.31 joules per mole. And notice that this is sort of, R is our constant that applies to number of moles. We can rewrite the same exact equation in terms of number of particles, and it just requires a different constant. So Kb is like the ideal gas constant. Remember, we've called it the Boltzmann's constant. But it applies to the number of particles, whereas R is per mole, and it applies to a mole of particles. So again, just watch out. There's 3 sort of versions of this same constant. Make sure you pick the right one. Let's just do a couple of quick examples here. Here's a quick clicker question. The 2 identical cylinders contain samples of gas. Each cylinder has a lightweight piston on top that is free to move. So the pressure inside each cylinder is equal to the atmospheric pressure. One cylinder contains hydrogen, the other nitrogen. Both gases are at the same temperature. How do the number of moles compare? Well, why don't you stop the video and peek at the ideal gas law and see if you can't figure this out. And I'll see you on the other side. Okay, well, let's check this out. Here's the ideal gas law. They've told us that the pressure is the same. They've told us that the volume is the same. They've also told us that the temperature is the same. Well, this is just a constant. So if 4 out of the 5 things are the same for one gas as they are for the other gas, then the 5th thing is also the same. They must have the same number of moles. So the point here is that in the ideal gas law, we don't really care what kind of particles we have. We don't care if they're hydrogen or nitrogen. We don't even care if they're water vapor, right? All we care is how many particles we have, the number of moles right here. Here's an example, and I'll do it kind of like a clicker question here. Again, for some of you, this is review, and so go ahead and give this a shot. We'll see how much of a review it is for you. So go ahead and give this a shot, and we'll do it here in just a second together. Okay, how many particles are in a spherical balloon with a radius of 20 centimeters? The gauge pressure in the balloon is 700 Pascal, and its temperature is 20 Celsius. Treat the air as an ideal gas. All right, well, there's a few things to be careful of. First of all, it's asking for the number of particles. So I'm going to go ahead and use this formulation. Recall that Kb, Boltzmann's constant, is the constant that's appropriate to use when we're looking for the number of particles. So our algebra is straightforward here. We just end up with PV over KBT. Tricky things to look out for here are the pressure. We should be using the absolute pressure. Well, what is the absolute pressure? Recall that in the previous segment, I gave you a conversion between atmospheres and pascals. And recall that 1 atmosphere is equal to 101 kilopascals. So, the gauge pressure is 7,000 Pascal. So recall that the absolute pressure is the gauge pressure plus atmospheric pressure. And so, what is that? Well, it is the gauge pressure, 7,000 pascals, plus the atmospheric pressure, which is 101,300 pascals. And so, we end up with okay, so just a quick reminder about the distinction between gauge pressure and absolute pressure. All right, so now let's go ahead and plug in our numbers and see what we get. Now, our N is P, which is 108,300 pascals. Again, we got to put in standard units if we want to get standard units out. Now, what is the volume? Ooh, they've told us that it has a radius of 20 centimeters. So we need to calculate the volume. The volume of the sphere is 4/3 pi r cubed. And what is r here? Well, we ought to convert it into standard units. Pi r cubed is the volume of a sphere. Divided by kb. Remember what kb is? 1.38 times 10 to the negative 23rd joules per Kelvin times the temperature. 20 Celsius? No. We need to use absolute, right? So we need to use 20 plus 273, and that will be in Kelvin. Okay, so I ran my calculator, and I got 8.98 times 10 to the 23rd. Okay. It's a lot of particles. You know, it's on the order of a mole and a half. Yeah, it's a reasonable number. I like it.